Hello there. This is chapter 4 video. I'm going to start with first few sections and continue, see how many videos we can have for chapter 4. I hope you're doing well. So let us get started on chapter 4. So here is what we want to do in chapter 4. Mainly is applications of differentiation that we talked about in chapter 3. So the first section is related rates. So let's get started. You can stop the video and read, and make sure we know what we're going to face in chapter 4. I'm sure you're reading the text as well, and you have access to the notes. So let's talk about related rates. In nature, we talked about that things in nature change. So in order to understand and study, in order to study nature, we need to reduce the number of variables that are changing. So we can't do that. We can't study everything at the same time. So in many application problems, we have this reductionist kind of approach to reduce the number of variables to only few so we can understand what's going on. Now, sometimes that approach actually is not good. For example, in terms of health of human body, you can't just reduce human body to just few organs or even one and study it. You just have to take the whole thing, right? And it's difficult to do that, but it's necessary in order to understand human health. But in many situations, we have no choice but to reduce the number of variables. So here in this example, what you see is a sphere that is getting bigger and bigger. So we're going to look at only two variables, the volume of the sphere and the radius of the sphere, right? And then we're going to concentrate on those two variables. So in related rate problems, that's what we are going to do. So let's look at an example. So the nature, of course, our interpretation of nature is what scientific interpretation of nature is the most reliable one. But even scientific interpretation is the best thing we can do. That doesn't mean reality. Reality exists outside of our heads. So the way we interpret it has nothing to do with the reality outside our heads. There is a reality out there. Whether we interpret it wrong or right doesn't matter. The reality doesn't care. In fact, reality doesn't care about us because we were not around when reality existed for a long time, right? All right, so let's see what related rates problems are all about. Here's an example. It says a spherical balloon is being filled with air at a constant rate of 2 cubic centimeters per second. How fast is the radius increasing when the radius is 3 centimeters? So you see here, the volume is increasing and the radius is increasing. We are going to assume that volume is a function of t and also radius is a function of t, right? So in order to do this problem, first we have to understand what variables are involved and also what is the relationship between the variables. So what is the relationship between volume of a sphere and the radius of the sphere? Well, we know that relationship is given by the volume of a sphere, right? Volume of a sphere, we've known this for a long time. Archimedes figured this out and he was so excited about it, and what he used was a sphere that was kind of inside a cylinder, right? So it was stuck inside a cylinder like that, kind of a sphere, kind of like that, and figure out the relationship between the volume of the sphere and the volume of the cylinder. He was so excited about that he wanted that shape to be on his tomb, and it was. Nobody knows where it is now, but that's his discovery. And so volume is 4/3 pi r to the third power. So the volume is with respect to t equals to 4/3 pi times r with respect to t to the third power. So now once we have a relationship between the variables, we are ready to take derivative of both sides. Now here variables are changing with respect to time. So we need to take the derivative with respect to time. So we're going to take the derivative with respect to time of both sides. So the derivative of v with respect to time, it would be just dv dt. And the derivative of 4/3 pi times something to the third is 4/3 pi, we keep that, times something, 3 times something to the second power, right? 3 times something to the second power, that's the power rule, times the derivative of inside, which is dr dt. You see, if we have x to the third power, d over dx of x to the third power is just 3x squared. But if you want to take the derivative with respect to t, right, and this is something with respect to t, then we're going to have to multiply by dx dt, right? Why? Because the variable of differentiation is not the same as that one, it's a different one. If that's the case, we assume this is a function of that variable. And then we have to take the derivative of it and multiply it. Remember, what do we call this? Did you say chain rule? Yes, that's what that is. It's chain rule. Okay, so what do we get? Well, we get what? We get dv dt equals to that. And so we got 1, 2, 3 unknowns, right? How many of them we are given? Well, we're given that radius is 3, and the rate of volume changing is 2 cubic centimeter per second. See, as the air goes inside, it turns into volume of the sphere, right? So the rate that the air is going in is actually the rate that the volume is increasing, right? So that's dv dt. So that's dv dt. We substitute for it. R is 3. We substitute for it. And dr dt is missing. We solve for dr dt. That's easy to do, right? Is 1 over 18 pi centimeter per second. So as volume is increasing here with this rate, the radius here is also increasing, but with a much smaller rate, right? All right. So here are the steps that we have to go through to do this problem. The steps are basically these are steps that you see over here, right? So we got, first we have to assign symbols to all variables that we are interested in. And if you draw a figure, of course, that would be nice. State in terms of the variables the information that is given. So we have to understand what is it that we are supposed to find and write it down. And then we have to find a relationship between the variables. That means an equation that relates the variables. And then we take the derivative of both sides, we find the related rates equation, right? So let me go back and make sure we understand that this equation that we found right here, this equation, that's the related rates equation. These are rates, and this equation relates them. So it's called related rates. All right. And then, of course, we substitute the known values and solve for the unknown value. Let's do one more. Here's another example. So what we have here is a particle moves along a circular path, and x and y are measured in feet. At point when x is 3 and y is 4, the rate that x is changing is 8 feet per second, we want to find what is the rate that y is changing, right? So that's the idea. So now part of this is done for us. The variables are already there, and the relationship between variables is given already. So all we have to do is draw some picture, maybe right here. So let me run this animation here and show you what's going on. You got a circular path, and an object is going in a circular path like this. So let me wait for it to. So you see, if I go around here, you see that x and a y are changing. X is this distance from here to here, and y is the distance from here to here, right? So you see what we have is what? How do we know that it's moving clockwise but not counterclockwise? Well, look, this is the point 3, 4, right? When x is 3 and y is 4. And we are told that at this point, dx dt is positive. So that means x is increasing. So this has to go this way for x to increase. But of course, that situation doesn't last. When you go over here, x actually starts decreasing. And of course, the same thing happens to y. Y is increasing here, decreasing here, right? So that's the situation. So let me go back and see how we can solve this. So it's much easier than the other problem because we are given the equation that relates what? That relates the variables. So we take the derivative with respect to t of both sides. What's the derivative of something is squared? Well, 2x dx dt. What's the derivative of something is squared? 2y dy dt. You got to multiply the derivative of the inside function, right? And what's the derivative of a constant? 0. So what do we have here is an equation that relates the rates. So that's the related rates equation. Once we have that, then we have to go to the problem and see what is given and what is missing. So we are given dx dt, we are given x and y, and dy dt is missing. So we solve for it. So isolate dy dt algebraically on one side. Everybody knows how to do that. You move all of that to the other side, change its sign, and divide by 2y. Now we can simplify. Just put this here. That's the same thing, right? So x is 3, y is 4, and dx dt is 8. So the rate is dy dt is negative 6 feet per second. That means when this object is moving over here, x is increasing at 8 feet per second, and y is decreasing at 6 feet per second. Now, this is not obvious, the answer to this, right? Without calculus, it would be difficult to actually figure out what's going on here. So that's the power of calculus. Let's do another problem. It says an airplane, it's flying overhead at a constant elevation of 4,000. A man is viewing the plane from the position 3,000 feet from the base of a radio tower. So there is a man here, and there is an airplane here that is moving, right? And there is a radio tower here somewhere, right? And the distance from the man to radio tower is 3,000 feet. And at any given point, there is a distance between the man and the airplane that is changing, right? So let's call that S. So S is changing, right? That's one variable changing here. So the airplane is flying horizontally away from the man. If the plane is flying at a rate of 600 feet per second, so this is changing, let's call this direction X, which is really the distance. If you kind of think of vertical shadow of the airplane down here, this distance is X, right? The distance from the man to this point is x. And then if it goes over here at this point would be another x, and then at this point would be another x, right? So there are two variables changing, s and x. The height, the altitude, the height of here, this height doesn't change. It remains what? It remains to be what? 4,000 feet, right? So the question is, when the airplane is over here, how fast this s is changing, right? Now, so this is a picture, and now you know why they say a picture is worth 1,000 words. You see the power of a picture right here. So let's look at some variables. There is s, there is x, right? There is the height that doesn't change. This is s of t, it changes with respect to time, and this is x of t, changes with respect to time. So here's the situation. Now we have to look at what is it that we are trying to find. We're trying to find what? ds dt, and we are given ds dt we are supposed to find. And we are given dx dt, and we are given this distance x. That distance is 3,000, right? So when x is 3,000, and when dx dt is 600, what is ds dt? That's the question. So let's do that. So what do? Well, we have to find a relationship between what? We have to find a relationship between s and t. Well, in this right triangle, we see that relationship is what? Pythagorean property. X squared plus 4,000 squared equals to s squared. That is the relationship between the variables. Now we have to convert that to related rates, right? How? We take derivative. Take derivative of that, we get this. Take derivative of that, we get 0. Take derivative of that, we get this, right? And we did a few of these already. You know why we get 2s ds dt. Now, how many unknowns? 1, 2, 3, 4. How many of them we are given? 3 of them. We are given x, right? We are given dx dt, but we are not given s, but not explicitly, but we are given the relationship between s and x. So we can find out what s is when x is 3,000, right? So we can substitute 3,000 here for x and find out what s is. So s is 5,000. So when s is 5,000 and x is 3,000 and dx dt is 600, what is ds dt? Right? And ds dt will equal to that. Right? You just substitute 3,000 here, 5,000 here, 600 here, and then isolate ds dt. That's what you get. So at that moment, the distance between the man and the airplane is changing at 360, right? Now think about it. In military weapons, suppose this is a bomber and people want to shut it down. And you have a device that sends something to hit this thing, right? If you want to do that, then you have to put all of these into a computer program, and that device has to be able to what? Figure out which direction to go to hit the target, right? Or maybe the airplane wants to hit a tank on the ground. You see, all of that can be automated by computers and using technology, of course. But the foundation of it is this idea. I shouldn't have used a war example, but that's the first thing came to my mind. I should have said about maybe you're dropping, food for people who need it at the bottom or something like that. All right, here's another one. A rocket is launched so that it rises vertically. A camera is positioned 5,000 feet from the launch pad. When the rocket is 1,000 feet above the launch pad, Its velocity is 600 feet per second. Find the necessary rate of change of the camera's angle as a function of time so that it always stays focused on the rocket. So you see, the rocket is going up here, could be over here, and the angle would be that much, or it could be, over there, and the angle is that much. So you see, the angle is actually changing, right? So one variable that is changing is theta, and is a function of t. Another variable is changing is the height here. So h is a function of t. There is also this distance from the camera to the rocket that is changing. We don't care about that in this problem. We're not told to care about that. So we're just going to leave that variable alone and not get it involved at all. We don't need to know it. So what do? Well, we have to write a relationship between what? We have to write a relationship between theta and h, right? So what is the relationship between theta and h? Well, we know the relationship is that the tangent of theta is opposite over adjacent. That's the easiest relationship we can write, right? You don't want to write sine of theta because that would be this over that. Then we have to get another thing involved, which is just not very wise to do, right? So tangent is h over 5,000. So h is 5,000 tangent theta, right? So what do? Well, we're gonna think of this as a relationship between the variables and take derivative with respect to time. So what's the derivative of h with respect to time? dh dt. What's the derivative of 5,000 tangent something? Would be 5,000 secant squared of something times derivative of something, right? Because that something is a function of t. If I take derivative with respect to theta, the answer would be just secant squared theta. But if I take the derivative with respect to t, then we have to get d theta dt involved, right? So that is related rates problem, see an equation, right? So 1, 2, 3 unknowns. So we need to find them. What are we given? We are given h, right? We are given h, and we are given dh dt, right? We want to find d theta dt, how fast the angle is changing. But we are given h, but we're not given secant squared theta. Well, we have to figure out how to get to secant squared theta from h equal to 1,000. So h equal to 1,000 means what? Means that at the moment when h is 1,000 here, right? This is theta here. So what is secant of that theta? Secant of that theta would be 1 over cosine. But what's the cosine of this angle? Cosine would be this over the hypotenuse. Now, this is not a variable, it's a constant, it's a number. We can find it. If this is 1,000, this is 5,000, we can find this number. In fact, I did it here. So this number is 1,000 square root of 26, right? I did it here. So by Pythagorean property, right? This is squared plus this squared equals that squared. So what's the cosine? Cosine would be this over that. What is secant is the reciprocal, this over this. So that's the secant, and we simplify it. Now remember, we want secant squared, so we take the square root, we get what? 26 over 25. So we put 26 over 25 here. Now we have only one unknown, we isolate it, and we get 3 over 26 radian per second. And remember, in trigonometry, in calculus with trigonometric functions, we use what? Radian unit, not degrees. Unless you have a conversion factor you always use radian. Okay, so the answer is 3/26 radians per second, and you can program some kind of mechanical device with, gears and stuff on it, and have it move with that velocity, right? You can convert that to like how many degrees. Maybe you have to move the camera per second, and maybe you have little gears here, and you can automate actually that this camera will move such that it's always focused on the rocket. All right, here's another problem. It says water is draining from the bottom of a cone-shaped funnel like this at a rate of 0.03 cubic feet per second. The height of the funnel is 2 feet and the radius at the top is 1. At what rate is the height of the water in the funnel changing when the height of the water is 0.5 feet? So, if the water is at 0.5 foot right there, right about maybe here somewhere. So if the water is at that level, then how fast is this h, which is the height of the water, changing? What's dh dt when the water is draining at this rate right here? Now right away this rate has to be negative. Why? Because it says 0.03 water draining, so the volume is decreasing at the rate of 0.03. So there are three things changing that we are interested in. The volume of this water, this is 3D, right? So there is a volume of water in here, and that volume is V. And there is the radius of the top surface of the water, R, and there is the height. So there are three variables, V, R, and H. And all three of them are what? Are functions of t, right? So we need to relate them. How do we relate those variables? Well, to relate them, we could just do what? Let me erase everything here. So we need an equation that relates all three of them. So what is the question asking us to do? Find dh dt when h is 0.5 and dv dt is negative 0.03, right? So that's the question. Okay, now we write an equation that relates what? That relates the three variables, the volume, R, and H. And that is, of course, the volume of a funnel. Now let me explain this here. If you have two bases, kind of flat bases that are the same, and you connect them, we get something we call prism in geometry. And the volume of a prism is basically the area of the base times the height, right? Now instead of having that circle, if we have a point right here, and then connect to all corners, of course this has infinite number of corners. If I connect to all of these, obviously we get what? We get this funnel. And so this shape right here, what's the volume of this? The volume of this is 1/3 of the volume of that prism that I just erased, right? So this prism. What's the volume of that prism? Is the area of the base times h. So that is the volume of the cylinder, and 1/3 of it is the volume of what? Is the volume of that pyramid. That's what it's called. Okay? So, and that is actually true for any prism or pyramid. So if the base, let's say, is a rectangle, right, something like that, if you connect these corners, what do you get? We get a prism, rectangular prism. Now instead of this, so the volume of this would be the base, the area of the base times the height. Now instead of that rectangle, if I just put a dot and then connect these, it would be a pyramid with rectangular base, right? And the volume of that would be 1/3 of that prism I just erased, right? So that's the idea. So the volume of that is 1/3 pi r squared h at any given h, and r, the volume, is given by that. So we found the relationship between the variables, but we have a problem because that relationship involves 3 variables and we can only deal with 2 variables. So what do we have to do? We have to get rid of what? We have to get rid of one of the variables. Which one? What is up to you? We can get rid of r or h. But in order to do that, we have to actually substitute an expression for one of them in terms of the other one. To do that, we come over here and we realize that if you look at it, that's why you have to draw a figure. You realize that this triangle here, that big triangle, right, and this is smaller one here, are similar triangles. In similar triangles, the ratios of corresponding sides are equal. So that means in this big triangle, 1/2, right, is the same as r/h, right? So r/h is the same as 1/2. That's it. We got the relationship. R is h/2, right? And now we can just substitute that in this formula. So r is h/2. So instead of r here, we put h/2. Simplify it. So we get what? We get that v is nothing but what? V is nothing but pi/12 times h⁻⁻. Now we take the derivative of both sides with respect to t. What's dv dt? dv dt. What's the derivative of pi/12 times something to the 3rd power? Pi/12 stays here. Something to the 3rd is 3 times h to the 2nd power times the derivative of inside, which is a dh dt. That's it. So this is the relationship between the rates. How many? 2 of them. 3 unknowns, but 2 rates. What are we given? We are given this rate, right? This is -0.03. We are given h, which is 0.5, and we want to find dh dt. That's easy. Just substitute the numbers here. Isolate dh dt. We get -0.153. So when the water volume is decreasing at the rate of -0.03 feet per second, oh, that should be a cubic foot per second. That's a unit should be cubic. Okay, then the height is decreasing at what? At this rate right here, right? -0.153 feet per second. Okay, that has to be to the 3rd because it's volume, right? All right, so that's it. That's how we deal with these problems. So I'm going to make another video to continue in chapter 4. I want to make the videos a little bit maybe shorter. So I want to talk about the rest of chapter 4 very soon. So for now, I want to come back here and say bye to you. And I see you in the next video. Take care of yourself and others.